Tell me. Hello.
Hello, sir.
Hi.
Good afternoon, sir.
Good afternoon. So can I start? Am I audible?
Yes, sir,
Let's
you are
just wait
audible.
for
Yes,
some
sir.
minutes. Like a few students are yet to join.
So have you studied any book for whatever we have discussed in our last class? Do you know what are the books to be followed? I think it is written on your syllabus, right? It is given.
Yes, sir. Yes, sir.
Mhm. So if you try, then you can also find the free PDF of all these books. I don't know whether Codeman is available or not, but the other three books are available. So if you do not get the chance to buy the book from outside, then you can try for the PDF. Okay, let us start because it is already 5 or 6 past 3. Uh, so last day, what we discussed, we have discussed about the necessity for studying this topic, design and analysis of algorithm, and an overview of what is an algorithm and different properties of an algorithm. Then we have got uh, some point that how to compute the time complexity of an algorithm by using the RAM model and so on. So there we have found that the time complexity of an algorithm, let Pn is written as like 4, I forgot, maybe the bubble sort is 4n square plus n plus some constant, say 6, let's. But we have found that the time complexity of an algorithm or mainly bubble sort is written as something like that, big O of n square. Now what is this? Okay. Another point is that is there any difference between 100n square plus 7n plus 80 and these two? Are these two equivalent in terms of time complexity or not? So because you see that if we plot this curve, so we will get a parabola. Maybe the origin is shifted or something like that. Similarly, 100n square plus 7n plus 80, if we draw, then also we will find a parabola of the same uh, uh, slope and so many things. The change is only in the origin, and if we can transform the origin from 0, 0 to somewhere else, then both the curves are nearly same, or we can say equivalent. So therefore, previously we have discussed that the time complexity analysis means to find or to compare between two or more algorithms. And there I have said that comparison means this polynomial comparison. So suppose one algorithm, say let A, is having the time complexity 4n square plus n plus 6, and another algorithm B is having the time complexity with the polynomial 100n square plus 7n plus 80. So the thing is that how to compare these two? Should we put the value of n equals to 1 to how many? Because we told that our input is very large, that is n tends to infinity. So if you put a very large n value, so you will find that these two constants are negligible. Similarly, these terms are negligible with respect to this one. This term is very negligible with respect to 4n square when n tends to infinity. Because of this, because both the polynomial is parabola. So whatever may be the value of this constant, the slope is following this equation, nothing else. If you go for ddn of this 4n square plus n plus 6 something, so you will get 4n. So that means a polynomial of n. Here also you will get the polynomial of n. So the slope of both the curves are same. Therefore, the rate of change when n tends to infinity are only depending upon this n, not on this constant and lower term. Okay. So therefore, we can say that these two may be equivalent. But how to draw this equivalency? So therefore, we require some bounds on these polynomials. Okay. Bound means again, last day we have discussed something about that. I forgot. What is that? Best case, worst case, and average case. Okay. So there is a relationship between all these. So best case means, in our previous discussion we have said that best case means the minimum value that we require to execute. So that means at least we require this much of value is given by best case. The maximum value is required to execute the algorithm is worst case, and average case means which is not dependent on the user input. Okay, and this is the expected value or probabilistic approach. But here we will not be able to say that best case means something, worst case means something. These two are different. So here our target is to find the bounds on these polynomials. Okay. So let us check that what are the different bounds that we can find on these polynomials. So first the term is written as asymptotic. All of you are aware that asymptote means we are considering for large value of input. So here already I have said that the large value means n tends to infinity. Okay. So where n is the input side. So first we will define the notations which is termed as big O. Okay, and is denoted as capital O. So what is big O? Big O is defined as let fx or fn and gn be two non-negative function of n. Okay, let fn and gn are two non-negative, that is positive function of n. So we can say that fn can be bounded as big O of g of n if and only if if and only if fn is less equals to some constant c into g of n for some or for all values n greater equals to n0. So what is the meaning of this? Later I will show the curve or the function diagram, the diagram of the function. But before that, let fn and gn are two functions, and we can say that fn can be bounded as big O of g of n if and only if fn is less equals to some constant, that is we have to find this constant multiplied by g of n for all values of n greater equals to n0. So we have to found n0 such that for all n greater equals to n0 this inequality holds. Okay. So let us consider one example. Let fn is equals to 4n square plus n plus 6, our previous example one. So can we write that this is less equals to let 5n square for, let us put n equals to 1. So for n equals to 1, from here we get 4 plus 1 plus 6, so that is equals to 11. But here we are getting 5. So therefore this inequality does not hold true. So for n equals to 1, this is not correct. Let n equals to 2, sorry, n equals to 1, this is not correct. For n equals to 2, what we will get? 4, that is 16 plus 2 plus 6. So that is equals to 4 plus 2 uh, plus 6, so 8, 24. Let us check this. 4 into 5, 20. No. So for n equals to 2, this is also not correct. Let us check for n equals to 3. So n equals to 3 means 9 into 4, 36 plus 3 plus 6. So that is equals to 45. Now n equals to 3, here also we are getting 45. So we can say that for n equals to 3, this equation holds true. Now if you put n equals to 4, obviously this one will be true, n equals to 5, again it will be true. So what we can write? We can write that fn is less equals to 5n square for all n greater equals to 3. So therefore we can say fn can be bounded as big O of n square for all n greater equals to 3. Okay. So that means we can say the upper bound here, big O defines the upper bound of the polynomial. Okay. So here Gn is defining the upper bound of the polynomial f of n. Upper bound means at most fn can be bounded with a polynomial of n square. Now you can say that why sir at most? That can be written like this. Here fn equals to 4n square plus n plus 6. Already we have proved that this is order of n square, and here previously before that we have said that it is 5n square for all n greater equals to 3. Now easily we can show that fn is 5 NQ also, or some other values. Okay, fn can be written as 5 n to the power 4 and so on. Now which one to consider? As per our definitions, we have said that fn is equals to big O of g of n if and only if fn is less equals to some constant into g of n. So here we are getting g as n square, n cube, n4. So which one to consider? So big O is defining the least upper bound. Okay. So among the all upper bounds, we have to choose the least upper bound, that is defined by big O. So here fn is defined as or bounded as big O of n square. And that means that if it can be bounded by big O of n square, automatically it can be bounded by nq, n4 and so on, any other higher values. Okay. So now if we consider Fn equals to 100 n square plus 4n plus 10, then also we will be able to find some value, say 110 or something like that. You can check it easily, n square. So therefore, we can say that this polynomial Fn can also be bounded as big O of n square. So with respect to the asymptotic notations, 4n square plus n plus 6 and 100n square plus 4n plus 12 is representing the same thing. Okay. So means only we are interested on to find this value, that what is the maximum value of this polynomial. So here we are getting this is n square. Okay. So the rate of change of both the polynomials are same. Therefore, we can convert these equations or polynomial to the order of big O, and which for this example these are order of n square. Similarly, you can write 5n plus 6 is equals to big O of n. Okay, and so on. Right. So here big O of n is providing us the least upper bound or the maximum value, we can say. Now, next, just like the least upper bound, we can find the greatest lower bound for any polynomial, given polynomial. So here the definition of big omega is that f of n can be bounded as big omega of g of n if and only fn is greater or equals to some constant into g of n for all n greater or equals to n0. Okay. So here in all these cases c is a positive constant, not non-negative constant. Clear? So we will not consider any negative value here. So therefore, as per the definition, what we are getting, fn is greater than this. So gn is providing us the lower bound for fn. So let us consider this example again. Fn is equals to 4n square plus n plus 6. So obviously this is can be written as 2n square for n greater or equals to 1. Okay. So easily we can check that this equation is true for n greater or equals to 1. So immediately we can write that Fn can be written as big omega of n square. Right. So the lower bound for Fn is given again as the order of n square. Similarly, 100n square plus 7n or something like that, it can also be expressed as the lower bound of n square. Now, just like the previous one, big O, again Fn can be bounded as the omega of n, because if it lower bound is n square, so the much less value also can be the bound. But here we will consider the greatest lower bound of all the bounds. So therefore, Fn equals to big omega of g of n. This gn is representing the greatest lower bound. So for this particular example, though omega n is the correct value for defining this Fn, but for whenever we will put this omega, so we will consider the greatest one, and which is omega of n square. Right. So therefore, big O is representing the upper bound, big omega is representing the lower bound. Now the thing is that upper bound means at most we may have this value, lower bound means at least we have this value. Okay. Now someone may say that why sir we should go for upper bound and lower bound? Is there any notations to find the both? Yes, there is a bound which is known as theta, and that is known as tight bound, because in theta we can define both O and omega. So now what is theta? We can write Fn is equals to theta of G of n if and only if. See here we are defining both the omega and O as C1 into G of n is less equals to f of n is less equals to some constant C2 into G of n. Okay, so this is defining omega, and this one is defining, this is defining big O. So add together, if we define both the notations, then we can say that this is true. Okay, so in our previous example, 4n square plus n plus 6, already you have seen that it can be bounded as big O of n square. Again, it can also be bounded as omega of n square. So together we can put this polynomial as theta of n square. Therefore, if we write that 4n square plus n plus 6 can be bounded as theta of n square, then automatically this one is true and this one is also true. So we don't have to go for writing both the notations, simply theta notations is fine. Okay. So you may ask that why we require big O and big omega. So theta is sufficient to define all these, but the problem is that in some cases it will not be easier to find both the lower bound and upper bound. Okay, just like say quick sort. Okay, we can find that the worst case is order of n square, the worst case time complexity of order of n square, but the best case time complexity is n log n. So here you see that we are defining the worst case means at most we require this, so we can say that big O of n square, and the best case means at least we require n log n, so we can write omega of n log n. So therefore we will not be able to say that the time complexity of quick sort is theta of n log n. Okay, we can say that average case time complexity of n log n is theta of average case time complexity is theta of n log n, but we have to prove it in other ways. But average case is not equivalent to theta. Don't mix up all these things. Best case does not mean omega. Worst case does not mean big omega, sorry O, and average case does not mean the theta. These two are different concepts. Best case means for a particular input how our algorithm executes, okay, whether it is good one or not. Worst case means how much what it can be or what is the maximum time to be taken. Here asymptotic notations are giving the bound of the polynomials. It is not finding the time complexity of the algorithms. Okay, time complexity of the algorithms are defined by best case, worst case, average case, and all these things. These are polynomials. To bound the polynomials, to find the upper bound and lower bound of the polynomials, we require asymptotic notation. So please don't get confused or don't mix up between best case, worst case, and big O, big omega. These two are different concepts. You have to read the books. Okay, then I think it will be much more clear to you. And theta means it is tight bound, which is containing both the upper and lower bound. So that's why it is known as theta. Okay, right. So now let us check one example like this. Let we are having a polynomial p of n is equals to root of n plus 5. Now what will be the bound for this? If we say that the upper bound is equals to n and the lower bound is equals to say root n, or maybe like this, so both are true, these are not false, that the upper bound of root of n is n, so at most this value will be a polynomial of n. omega of quadrat root of or fourth root of n. Obviously, if root n is the polynomial n to the power half, so n to the power 1 by 4 must be the lower bound or maybe less than this. Obviously. But you see that though n is the upper bound, but can you say that this is a tight upper bound? This is not a tight upper bound. That means it is a very loosely binding the value. Similarly, we are finding the loose lower bound for the polynomial. So though these are correct, but these are not the tight. Tight means not so closer. Yes, it is upper bound. So just like this, if I have required to sleep this much of space, if you provide this one, it is fine. But this is not optimal one. So which one is optimal here? So therefore, sometimes it is not possible for us to define the tight upper bound and tight lower bound. So we have another two asymptotic notations, though these are not very famous or you will not find regularly in your book, but still we require to learn these two. One is small o. Small o is defining as that Fn can be bounded as small o, which is defined as small letter of o, of g of n if and only if limit n tends to infinity Fn by Gn is equals to 0. Okay. So here we are saying when n is very large, the ratio between these two is negligible and tends to 0. So here in this case, let the polynomial is Pn is equals to root of n plus 5. So if I say that this Pn or let Fn by Gn, we are considering Gn equals to n, root n plus 5 by n, and we take limit on both sides tends to infinity. So here we get that limit n tends to infinity 1 by root n plus limit n tends to infinity 5 by n. So this is 0, this one is 0. So that is equals to 0. Okay. So now see what we have defined. We have defined that this polynomial is denoted as or bounded as small o of n. Previously we have said that big O of n, which is a loose upper bound for that, and to define the loose upper bound we are saying that this is small o of n. Okay, small o of n. So small o of n or small o is defining the loose upper bound. Similarly, we have the loose lower bound, which is known as small omega. So here it is just the opposite. We can say that Fn equals to small omega of g of n if and only if limit n tends to infinity g of n by Fn is equals to 0. Okay. So you can choose like this any lower value or upper value, upper bound for this small omega, lower bound, and small o for upper bound. These are tight or closer upper bound. This is closer lower bound. This is loose upper bound, and this is loose lower bound. These two are defined by theta itself. Clear? So these five are the asymptotic notations that we will use throughout our discussion. Among these, the first three are very much popular and these two are less popular, but sometimes we require to define all these. So let us go for one plot so that you can find what is this. So actually, let this is the Fn given any polynomial, right? Any polynomial that is given here. Now we are finding the lower bound and upper bound. What is the meaning of this? You see that for a particular n0 that we have found here, before that we are not considering anything. That n0 may be 1, no problem. So for a particular given n0, after that this curve is always under than this. So whatever value you get from C1 into G of n always will be less than f of n. So this is defining omega of n. So we are finding a curve or polynomial which is always less than this. Similarly, for big O of n, we are finding not n, sorry, g of n, we are finding a curve which is always greater than f of n. Okay, so here generally we are finding the upper bound which is a polynomial or a curve always will be higher than fn, a curve or a polynomial which is always will be less than the given polynomial. So if both are defined by g of n, then we can say that this is theta of g of n, right? So this is the concept of asymptotic notation. Just you go through any book. If you find any difficulty, let me know in the next class. Again, I can give some idea of that. Okay. Then. So then, what we have studied? We have studied that what is an algorithm, how to compute the time complexity of an algorithm. Then we have learned that how to find the bound for this polynomials or the equation. Okay. So then, now instead of only the RAM, that is random access machine, here we will discuss that how to find the solution or the time complexity of a recurrence. Okay, all of you are aware about the recurrence, these recurrent functions and all these. So let us first consider one example, say merge sort. I think all of you are having the idea of merge sort. In merge sort, what we do? Generally, we make a partition of something like that. M equals to, if n is the total number of elements, then we consider n by 2. Then we call the same function merge sort with 1 to m, and the merge sort with m plus 1 to n, like this. Okay. Then we call a value function like this merge sort with all these values, something like that, and this is the uh, algorithm of merge sort. So for merge sort again, or for merge or something, if this is merge sort and this is merge sort, this one is merging or something like that. So we write a merge function here. So if you can remember, here we have a function for I equals to 1 to n, and we do some comparison and merge all these elements, nothing else. And merge sort are called twice, one for half and another for half value. Now, how to define the time complexity of this algorithm? First, we have to find out the equation that how to define this time complexity of the merge sort algorithm. After that, we will go for solving these recurrences. So, we need some recurrence relationship, okay, or recurrence relations, or we can say recurrence equations, or simply recurrences. So, here we can write like this, that let Tn be the time complexity of merge sort. Okay, then what are we doing? We are calling the same function with half of the element first, then again we are calling the same function with half of the element. So if Tn is the time complexity of this merge sort algorithm, obviously Tn by 2 will be the time complexity of this one, and Tn by 2 will be the time complexity of this one. And if you calculate the time complexity of merge by using RAM, that is random access machine model, then you will find that there are n number of executions and some assignment values. So it is a polynomial of n. So we can write n only. For the simplicity, you can write some constant into n also, no problem. Okay. So just like this, the sum value into n. So here Tn can be expressed as Tn by 2 plus Tn by 2 plus T of n. Now the question is that is equal to Tn by 2 plus a polynomial of n. I am discarding this value for the sake of simplicity, nothing else. We can write this, no problem. But already we have learned that any polynomial, say 4n plus 5, can be written as a polynomial of n only in case of finding the time complexity. So now we have got the time complexity or the recurrence as Tn equals to 2Tn by 2 plus n. Now the question is that how to solve the problem. Okay, so that is the term solving recurrences. To solve the recurrences, we are having three different kinds of methods. One is known as the substitution method. So today we have some time. Substitution method uh, says that, or it suggests that first we have to consider a solution for the given recurrence. Okay. So first we'll assume a solution that may be correct one, that may not be correct one. But first we have to assume a solution. Then we have to check whether our assumption is correct or not. So this is substitution. That means first we will assume one solution, we will substitute the solution into the equation. If the equation gives us that yes, our assumption is correct, then fine. If not, then we have to change our assumption and we have to go for the next proof. Okay. So this is the main motto of the substitution method. So let us write an example. Let us go for some example, then I think it will be clear to you. So let us consider the March sort itself. So what is the March sort equation? Tn is equals to 2t. We can write the floor value of n by 2. I think all of you are aware that what is the floor value. Floor value means just less than n by 2. Okay, so that means if this value is greater, it will be less than n by 2, but the largest integer which is less than n by 2. So that is floor value, and the ceiling value is the largest or the least integer which is greater than n plus 2. So let Tn is equals to 2t floor value of n by 2 plus n. We for the simplicity we can omit this term, no problem. Okay, but since we have to be habituated with all these terms, that lower value or floor value, ceiling value and all these things, therefore I have considered this one as the equation for our example. So since I am teaching for the last 20 years, so I have a lot of experience, therefore I can assume a good solution. Let us consider. Okay, so later I will say that how to calculate or how to find the good solution. The one thing is that I have lot of experiences to solve lot of recurrences, therefore I can guess a very closer solution. Number one, so experience matters for selecting the correct assumption. Okay, so the assumption is let our assumption is Tn equals to, that is solution is big O of n log n, right? So just keep a note here that we have to ask sir that how you have assumed this one as the correct, because later we will be able to prove that yes, this is the correct assumption. So take a note that later we will ask the question. So I am assuming that our solution is Tn equals to big O of n log n. So as per the definition of big O, what we can write, Tn is less equals to some constant into n log n. As per the definition, already we have read this, that our sorry, just a minute. So our assumption is sorry, okay, yes. So this is n log n. So from the definition we can write Tn equals to this. Therefore, Tn by 2, floor value of n by 2 can be written as C into n by 2 log of n by 2. So whenever, one thing is, whenever I will write Lg, please consider this is log base 2. Okay, in next I will not write this log base 2. Whenever I will write Lg, consider this is base 2. If I write Ln, consider base 10. And if we write any other base, then I will write log then base. Okay, right. So Cn by 2 is this. Now substitute this value to the given equation. So what we will get? We will get Pn is less equals to 2 C n by 2 log of n by 2 plus n. Okay, simply we have replaced. Replace means substituted this one. So here we can write 2, sorry, not 2, uh, 2 will be erased. So we can write C n log of n by 2 plus n. So we can write less equals to C into n plus 1 log of n minus Cn into log of 2 plus n. Okay, so that equals to Cn plus log n minus Cn, sorry, Cn log n plus C into log n minus Cn plus n. Okay, so here we have got, because we know that the floor value of n always will be less equals to this. So what are what we are getting? We are getting that it is equals to Cn log n plus C log n minus Cn plus n. So we can write this is less equals to Cn log n minus, we are writing C minus, if I do any mistakes, please let me tell that this n plus log of n. So we can write this is equals to, sorry, not less equals to Cn log n minus C minus 1 into n minus log of n. Okay, then if we consider a value of C and n such that C minus 1 into n minus log n, C minus 1 into n minus log n is, this is greater equals to 0, this part, because we can choose a value of C here which is greater than 1, and this value, if for any large value of n, obviously n is much higher than log n, therefore C minus 1 into n can absorb log n, and this whole term will be greater equals to 0. So if this term is greater equals to 0, can we write that this is Cn log n? Okay, Cn log n. Now see, what we had assumed, that our assumption is big O of n log n, and here we have found that yes, for this assumption Tn is less equals to C into n log n. Therefore we can say our assumption is correct. Clear? So assumption is correct. We can say that the assumption is correct, but here we have proved the half of the assumption. Okay. So here just we have considered big O of n log n, and we have shown that yes, Tn is less equals to Pn into log n. Therefore, theoretically this is correct, but we have to check this with the values. How? Say, here the equation is Tn equals to 2t n by 2 plus n. You can consider the floor value, no problem. And your assumption was Tn is less equals to some constant into n log n. That you have also proved here, okay, by substitution. Now consider n equals to 1. For n equals to 1, from here we will get t of 1 equals to 2t half plus 1. So half means no value, because we cannot execute any algorithm with half of the element. That is half element, not a single element also. So this is immaterial 0. So we can write t1 is equals to 1. Now let us check here. t1 is less equals to some constant, any value constant, into 1 into log 1, which is 0. So this is 0. Therefore, you see, from the left hand side you are getting 1, and from right hand side you are getting 0. Therefore, this assumption is not correct for n equals to 1. Just think about, we are finding the n0 value. Now consider n equals to 2. So here we will get t2 is equals to 2t n by 2 means 1, 2 by 2 1 plus 2. So that equals to, from here we have got this one is 1 and this is 2. So we got 4. Now check this. T2 is less equals to some constant C 2 log 2. So that is equals to 2C. Now you can say that yes, if we consider C as 2, then it is correct, right? So let us consider for C equals to 2, T2 from the left hand side 4 and also right hand side 4. Very fine. Now consider n equals to 4. Check. So n equals to 4, whether for C equals to 2 this is correct or not. For n equals to 4, what we will get? 2t n by 2 means 2 plus 4. What is the value of t2? Already we have found 4. So 2 into 4 plus 4, that is equals to 12, 12. And here Tn is equals to C. Already we have found from here 2, the value of C is 2, n 4 log 4. So we can get this value is log 4 means 2. So 2 into 4 into 2. So 4 into 2, 8, 16. Yes, correct. Okay. So Tn 12 is less equals to 16. So this is true. Therefore, for C equals to 2 and for all n greater equals to 2, we can write that our assumption Tn equals to big O of n log n is correct, and hence this is the correct solution. Okay, right? Very good. Now you can ask the question that how we can assume the correct solution, right? Do you have this question?
Yes, sir.
So how to go for a correct assumption? That is the main thing, because everything is written on the book and I have copied from the book, or someone is copied from the book, or someone downloaded from the internet or something, and it is very easy to go for the assumption. But during the practical or maybe exam, or when the equation is unknown to us, how to go for correct guessing, that is the main problem. And after discussing this, we will stop. Do you have the class now?
Sir, we have theory of computation class after this.
So from
4:30.
switch off करो microphone. Microphone off करो. हाँ ठीक है. Thank you. So now let us check another example. Then I think you will get your answer that how to go for correct guessing. Let we are having an unknown equation Tn equals to 2t n by 2 plus 55 plus n. Should not write 50. Let n. So what will be the solution of this? Now just a few minutes back I said that I have lot of experience for solving all these. So here you are also having some experience to solve at least one problem that we have discussed. Okay. So you check that our experience told me that we have an experience to solve this problem. Now check, if we compare, we may get some kind of similarities between these two except a term 55. Now think about when n tends to infinity is very large, 55 is very negligible with respect to infinity. Therefore, can we assume that if the solution of this equation is big O of n log n, then the solution of this equation may also be big O of n log n? Because 55 is very negligible and it will not make any change to your time complexity or solution. Therefore, from your previous experience, you can go for selecting or choosing the correct assumption. If you put this value here again as previous, whatever we have discussed, you will find that yes, this assumption is also correct for this equation. Okay, this is one way that your experiences will help you to go for correct assumption. There is no such method or mathematics for choosing the correct assumption. Number one. So your experience matters. Next, this one is another helpful method or way to go for correct solution. Let the equation is given as t root of this plus log of n. Check. Here the power of n is to the power half, and we have our experience with n, that is n to the power 1. So what can we do? We can change the variable as this. Let us consider m equals to, or sorry, let us go for this, n equals to, right? Let us consider this value as n equals to 2 to the power n. Let us choose this. Okay. So then what we can write from here, we can write Tn is equals to 2t, or this one instead of n we can simply write this one also, t of 2 to the power m, sorry, 2t 2 to the power m by 2 plus this one is log n means m. So can we convert this equation if we consider n equals to 2 to the power m? Yes. So now we are changing this variable by considering Sm is equals to t of 2 to the power n. So if we change the variable of the recurrence, then this can be converted as S of m is equals to 2s m by 2. See, if Sm equals to T of 2 to the power m, 2 to the power m by 2 must be written as m by 2 plus m. This is not dependent on s. Now check, this is known to us. And we know the solution of this equation is big O of m log of m. Just replace the value of m. So what we will get? The solution of this equation is big O of m means log n log of n. So this is the solution. So changing variable is another method for correct guessing. Sometimes if we get some equations like this, we can change the value and we can go for correct guessing. Okay. Now I am giving a wrong proof of the substitution method. Check it very carefully. That only proof is not sufficient. This is necessary that our assumption is correct, that we have to prove by substituting the assumption in our equation. But this is the necessary condition, not the sufficient. We have to check with the values, that is the sufficient condition. If both necessary and sufficient conditions are met, then only we will be able to say that our assumption is correct. Let us consider one example here. Let the equation is given as 2t n by 2 plus n. Again, let's store value. Okay. Let us consider the assumption is Tn equals to big O of n. So as per the definition, this is equals to c into n. Now let us put this value. What we will get? 2c n by 2 plus n. Simple. So that is equals to cn plus n. That is equals to c plus 1 into n. That equals to some constant c into n. Therefore, our assumption is correct, because as per the definition t1 is less equals to some constant into n. So we can write Tn equals to big O of n is a correct guessing, but not. This is not correct. Number one, here your constant was c and here your constant one is c1. So we are not considering the constant term, though we are saying that c and c1 both are constant, but these two are different constants. Now how to check that whether these two are different constants? Let us check for this. What we have? Let us erase first. So we are having Tn is equals to 2t n by 2 plus n, and here Tn is less equals to some constant into n. So let us check for n equals to 1 first. N equals to 1. From here we will get only Tn equals to 1. Already we have proved that this will be 0 and this is 1. And here we get Tn is less equals to some constant c. Okay, for n equals to 1. So if we consider c equals to 1, this is true. Forget about that. If you consider n equals to 2, let us check. So for c equals to 1, we can write that Tn is less equals to Cn. Tn means not only Tn, we have to write this value. We have to write this value, that 2Tn by 2 plus n is less equals to Cn when c equals to 1. This is true. From here we can get. Now let us check for n equals to 2. What we will get? Tn equals to 2t n by 2 means 1 plus 2. That is equals to 2 plus 1, 4. Now check here. Tn is equals to 1, or sorry, less equals to 1, because c equals to 1 and this is equals to 2. So from here we are getting 2. Therefore, we can say that 4 is less equals to 2, which is wrong. Therefore, though we have proved that big O of n after substitution big O of n is Tn some constant into n, but this is not the correct casing. Why? Because the necessary condition is okay, but the sufficient condition for finding n equals to n0 and a value c is not correct. Therefore, when we have to prove the assumption is correct or not, we have to go for both necessary and sufficient conditions. Then only we will be able to find the correct casing. So what we have got from our discussion? From our discussions, we have got that we are having substitution method where we will guess a solution, we will substitute this value in the equation and check whether the substitution is correct or not. Next, for the sufficient condition, we have to check that whether for the values of c and n0 this inequation is correct or not. If yes, then we will say that the correct guessing is correct. Number 2, that how to go for correct guessing. One is experience, and next is some tricks like change of variables and others. Okay, change of variables. Another point is there that for a guessing, let us select, suppose Tn is equals to 2Tn by 2 plus n, you don't have any experience. Then what we can do? We can start from big O of n and we will find that this is not correct. Here we can start with big O of n square, we can say that this is not also correct. So here we find that Tn is greater than big O of n and Tn is less than big O of n square. What does it mean? It is in between somewhere. So you increase the lower bound and decrease the upper bound. In another case, you can go for proving this, that whenever you are not getting anything, so you do one thing, you guess a lower bound and you guess an upper bound, okay, and check whether this lower bound is correct or not. If yes, and this upper bound is correct or not, if yes, then you increase the lower bound and decrease the upper bound. So here in between you will find that it is n log n, and you check for this value. Okay, also you can check for omega of n log n, no problem. So you may find that both are correct, then it will be theta of n log n. If not, that only the upper bound is correct but lower bound is not correct, then you can say that the upper bound is big O of n log n but the lower bound is not n log n, right? So there are three: experience, change of variables, and find the lower bound and upper bound, then increase the lower bound and decrease the upper bound. That's the method.
Sir,
Okay.
sir, 2 into, sir, let us consider the solution of this equation to be n. So we
Which
can
one?
say, yes, sir, Tn. So let us consider for once.
This one, Tn is equals to 2Tn by 2, sorry, plus n.
Yes, sir.
Okay.
So if we consider it to be, let's say n, Tn equals to n.
N equals to not n, either big O of n or omega of n. बोलो
So
कौन सा?
let's say big of n. So sir, 2 into n by 2 will always be lesser than or equal to n. So we can say that.
2 of
Take the
n
2
by
in, yes, sir.
always will be less than n.
Yes, sir. 2 into n by 2, because n by 2 is the floor value and 2 into n by 2 will be lesser than n. So
That is
n,
no problem.
yes, sir. So n plus n, that is 2n. So if we take c equals to 2, so our conditions are satisfied. So
Yes,
why?
no problem. So n plus n is less equals to 2 into n. So we are considering c.
C
ठीक
equals to
है?
2.
C
Yes.
equals to 2. Okay. Now consider n equals to 4. Then
Sir, 4 by 2 is 2, and 2 into 2, 4. 4 plus 4, 8. And 2 into 4, 8. So valid.
And for higher values, check all these.
Yes, sir. So n by 2, floor value of n by 2 into 2 will always be lesser than 1. So.
Number 1, for n equals to 1, this is not correct. Though we are getting one solution C, right? So this is not correct. Number 1. Similarly, later you please check for other values of n. So initially this is not correct. I will not go for choosing the next value. For C, you can go for choosing the next value of n0, no problem. But here when n equals to 1, we are getting some value of C which is satisfying the equation Tn is less equals to C into n, right or not?
Yes, sir.
So that is the main thing. If it is for, okay, we are considering some value of constant which is given, we are not getting the value of n0, then we can go for n equals to 2, n equals to 3, n equals to 4, as in our previous case, right? But the here question is to find the C only. So for n equals to 1, n equals to 1, since this is true, therefore we are getting C equals to 1. But for the next iteration when n equals to 2, this value of C is being changed. Got my point?
But sir, we can consider C equals to 2 throughout the process. There's no harm in it.
No, that will not be possible. You check it with some other values, you will find the fault here. Okay. Still, if you do not find that where is the problem, next day again you tell me, I can repeat it.
Okay, sir.
Okay, but please check it with some more values that this will not be correct one. You will get that why. Maybe you are not being able to catch it now, but please check it with some more values that why if we consider C equals to 2 from the beginning, then why it will be wrong. And even for C equals to 2, you may find that C is not equals to 2 for some higher value. Okay, when Cn equals to n. Clear?
Yes, sir.
With some value. So then I think it will be much more clear. If not, suppose if you have, even after reading the books and others, still if you have any difficulty, then next day at the beginning raise your hand and say that, sir, I have not understood this, please repeat. I will repeat the same thing again. Okay.
Okay, sir.
Okay. So next day, if required, I will repeat the substitution method again, and after that we will go for iterative method and the master method. But my again to all of you, don't wait for the exams and don't wait for some other thing. Just collect your books from anywhere and start reading from the first chapter. Okay. Generally, I prefer to teach from the Coreman and Sahani. There are few chapters that I will take help of Bhagirani and some other books. I will tell you later. Also, all these books are given in your syllabus or curriculum. Check the curriculum. Only 3 or 4 books are there, and I will just go for from this. I will teach. So collect all these books, start reading. Otherwise, at the end, before exam, if you go for winding up all these together, then it will be a hodgepodge and you will not be able to learn anything from this topic. But it will be required throughout your life, whether you go for industry, whether you go for teaching, whether you go for any research oriented industry job, anywhere you go, this topic will be required throughout your life as a computer science engineer. Take it this as very serious and read it carefully. Okay. So let us
Yes, sir.
of this class for today. Next day, I think Monday is our class from 3 to 3:45 or something. I will check. and give you the link. Right? So how to